Assalamualaikum warahmatullahi wabarakatuh and good day everyone. Okay, today we're going to learn our chapter 10, last chapter for this semester, which is numerical integration. The reason why we want to use numerical integration is the same as the previous chapter. Why we want to use the numerical differentiation is because we don't know actually the function. Okay, and also when a function is quite difficult to integrate. That is where we want to use the numerical integration. One best known example is where we want to find the area under the curve. Okay, let's say we have this curve like this, right? So let's say the area under here that we want to find is hard to find it using integration. Is that to integrate it, to find the integration. That's why we need to use the numerical integration. Okay, because we use the numerical integration, we know that this is not the direct answer. Okay, this we do when we do numerical integration, we will approximate the integration. Okay, the answer will not be the direct one. Okay. Okay, now we move towards the numerical integration and the method that the formula that you will learn in this class. Okay. We will go one by one. So we have three actually. The first one is the Trapezoidal Rule, followed by the Simpson's Rule, and then the Romberg Integration. Okay, we will go through one by one. The first rule that we're going to see is the Trapezoidal Rule. The Trapezoidal Rule is equivalent to approximating the area of the trapezoid under the straight line connecting FA and FB. As I mentioned before in the introduction, we want to find the area under the curve here. So we can use it by using a trapezoidal rule between the FA and FB and the A and the B here. So this is a trapezoid form, right? But as you can see, if we use trapezoid like this from point A and point B, have FA and FB, we have some error here because it will calculate under this one. But this is the error that we have. Okay, because we using this trapezoidal, this will be the error because we cannot find the correct answer because this is the approximation, right? So the error is quite big. So how can we reduce the error? So we can count as we can approximate as good as possible the area under the line here, under the curve, because as you can see the error is quite big here, right? How can we make it more approximate, more accurate? As you can see here, one way to improve the accuracy of the trapezoid rule is to divide the integration interval from A to B into a number of segments. Okay, the areas of individual segment can be added to yield the integral for entire interval. So as you can see here, before this we have FA and FB from A to B, right? But now we have a smaller trapezoidal here. So we have 1, 2, 3, 4, 5 trapezoidal, small trapezoidal, right? So you can see if you do it like this, the error becomes very small here. Okay, so we can minimize the error. So we can better calculate the area under the curve here. Okay, so there are n plus 1 equally spaced nodes. So we start with x0, right? This is your x1, x2, x3, x4, and x5 until, if you have more, until xn is the last one. Okay, so we have x0 until xn depending on how many is your trapezoid. So you can see if you want to make the trapezoidal approximation accurate, more accurate, you need to add more trapezoidal, okay, towards the under the area under the curve. The more trapezoid, the more accurate your calculation. But of course, if you want it more accurate, there will be more calculation because there will be more trapezoid. Okay, I think you already remember from previous chapters also. The more points, the more trapezoid you have, the more accurate it be, but the calculation will be more long and complex. So if you can see here, instead of we have just one long from A to B, right? So we have a smaller one from x0 to x1. If you remember previously, we have x0, x1, x2, x3, x4, and x5, right? So instead of calculate directly A and B, the trapezoidal form, so we do it smaller trapezoidal way. So x0 to x1, x1 to x2, until so on xn to xn minus 1. Okay, so this is how we make it more accurate. Okay, this is the where they derive the formula that you will use in the trapezoidal rule. Okay, this is where they derive the formula. As usual, in this class, we will not be too concerned about the derivation. We will need you to understand how to use the formula given to you. Okay, but for summary here, we can see the solution here, the equation is based from the polynomial. Okay, and they will use the polynomial as the fx here to solve the integration problem. This is the continuation of the derivation process from the previous slide. Okay, as you can see at the end there, this is the formula for trapezoid. Okay, so if we can illustrate, all right, okay, let's say this is your trapezoid, right? This is your edge. Look into the formula. Okay, I try to see the formula in terms of the illustration. All right, this is your xk, this is your xk plus 1. The up here, the length here is the fk. This is your fxk, and this is your fxk plus 1. Okay, actually this is a formula for trapezoid, hence the name trapezoidal rule. And this is for one equation for one. Let's say this is 0, 1. So this is just for the one interval. Okay, the first interval. If you have many intervals, that's why you will have plus here. If you see down here, this is where if you have more than one interval. Okay, this is the first interval, second interval, as I mentioned before, right? Let's say the area under the curve here. So if you do trapezoidal from this point to this point, let's say, so this is your first, second, third. So this trapezoidal here, so this is the first, the second, and the third. So you need to add them, okay, until end. All right, that's why you will have a long calculation if you have more trapezoid. Okay, more smaller trapezoid that you will have a longer calculations. And then this is the final formula that you need to use based from the summarization of this formula. Okay, of this formula. Okay, let's look at the example here. Approximate the following integral using trapezoidal rule with h is 0.5 and h is 0.25. So we have to calculate for h 0.5 and h 0.25. Okay, so here this question, they give you the fx. They give you your fx is x plus 4. Okay, your a is 1, your b is 4. Okay, they give you this this fx here. Sometimes they also they will not give you the fx, same as previous class, previous section, previous chapter. Okay, sometimes they don't give you the fx. They will give you in terms of table. If you remember, this is your x, this is your fx, and this is the number for xfx. Sometimes they give you the table, they don't give you the fx. But for this question, they give you the fx, so you need to calculate to find the that you can make it into a table. So two ways, alright? Sometimes they give you fx, sometimes they don't. If they don't, they give you the table. Okay, as I mentioned before, this question give you the h, right? And sometimes they give you the n. Okay, it depends. Sometimes the question give you h, sometimes the question give you n. So you can find them, alright? Just replace it here. Okay, if they give you n, put n here, h up here. So you can find your h. If you give you h, you can find the n. Alright, depends on the question. So the first thing you need to do is you need to make this table. Okay, you need to make this table to solve chapter 10 here. I want to see this table. Okay, this is the trapezoidal table. Okay, if you see here, we have n is 6, right? So the point should be 7, n plus 1, right? We start with 0, right? So 6 plus 1 is 7 points. So we have 0, 1, 2, 3, 4, 5, 6, 7 points. Okay, remember we start with 0. Alright, so our n, if we have 6, means that 6 plus 1, because we need to count the 0. Starting is 0. Okay, so this is your h here. So we have 0, 1, 2, 3, 4, 5, 6. We have 7 points. And this is your h is 0.5 between these two. Okay, 0.5, right? For each of them. It must be for chapter 10, or the h must be similar. The h must be the same. Okay, it must be same as from all of it. Okay, it cannot be different, the h. Right, 0, 1, 2, 3, 4. This is your n, this is your a, and this is your b, and this is your h, so on. Right, then you need to calculate the fx of each of the points. Let's say here is 1.0, right? So f 1.0, so equals to 1.0 divided 1.0 plus 4. Okay, and then you will get your answer for this one. And then do it for all of it, for all of the points. Okay, using the formula here. Then for trapezoidal here, okay, for the first and last, it should be in this column. Okay, this column for the first and the last one here. Let's say the first here is 0 and the last one here is 6, right? And 6. So two of them should be in this column. In the middle should be in another column. Okay, in this column. So the number 1, 2, 3, 4, 5 in the second column. Alright, and then you make a total of both columns. This is the total for number 0 and 6. Okay, and this is the total of from 1 to 5. From 1 to 5 here. Okay, make the total of both of them, both column. Okay, this is then after you finish with the table, you need to calculate the results, the approximation. Okay, why we have two column before in the table? Because of here, this is your f0 and f6. All right, this is the first column summary, the total 1.864, and this is the total of the middle, all the middle row from 1 to 5. So this is the total. Okay, if you remember our formula before, why is it like this? Because our formula before is h2 f0 plus fn plus 2 summary of I equals to 1n minus 1 fi. So this is your f0 and f6 for this question. Yeah, the first one f0 and fn. Our last one is f6, and then this is all the sum of in the middle from 1 from n minus 1, okay, until fi I equals to 1 until f5 here. So 1 until 5 will be in the second one here. This is for the first and the last. This is everything in between. Okay, this is based from our previous formula in the previous slide. You can check it out. Okay, and then you get your approximation is 2.8896. Okay, same thing, but this one, if you remember the question, they asked for 2h, h0.5 and h0.25. This for h0.25, and if you do the calculation for the n here, you want to find the n, right? So you will get 12n. So 12 plus 1, so you get 13 points because of the 0 here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 points. Okay, n plus 1 because we start with 0. Remember that. And then the h is 0.25, right? So this is your n. Okay, and then this is your h for every one of it is 0.25. Okay, and then this is your a, this is your b. Okay, same as we do before. We calculate this one, right? So the calculation same is f 1.0 equals to 1.0 plus 4. Then you get your answer. And then as you notice, before this we have two columns. Same here, because this is the same method we done here, trapezoidal. The first one 0 and the point number 12 here. Okay, point 0 and point 12 all in one column. So this is the sum of these two, and everything in the middle from 1 to 11 is in the second column, and you calculate the sum of it. Okay, same as previously, but this time of course the h here is 0.25, so we will have a lot of double the amount of the n, right, because of the smaller h, so that you will have to do much more calculation here. Okay, then after you finish with the trapezoidal table, you need to insert the sum into both here. This is the sum for the first and the last one. This is the sum for everything in between. Okay, and then you calculate your answer. And the exact value integral is 2.8925. This is the exact value. No, not the estimation that we have count. This is the exact value. Okay. And then if you can see for h 0.5, n is 6. And for h 0.25, n is 12. The error is 0.029 for the h 0.5, and h 0.25, the error is 0.007 if you minus the exact value that we have stated before. So as you can see, the error decreases as the number of segments n increases. So when h is reduced by a factor of half, the successive errors are diminished by approximately a quarter. So the error is diminished if you have much more n. Much more trapezoidal that you have, the less amount of error that you will encounter in your approximation. Okay, but of course, a lot more calculation that you need to make. Okay, now we move to the second rule, which is Simpson rule. As we know, trapezoidal rule usually requires a large number of function evaluation to achieve accurate answer. Another way to obtain a more accurate estimate of an integral is to use higher order polynomials. Okay, if you can see, before in trapezoidal we use only these two, right? But for Simpson rule we add another formula inside the trapezoidal before to improve the trapezoidal rule. okay, inside the polynomial here. So the polynomial for Simpson much more complicated with more added points here. Theoretically, if we expand our polynomial, okay, such as like this, we will get a more accurate answer. Okay, this is the derivation of the formula for Simpson rule. Right, as we know, this is from our trapezoidal, and this is the one we added into the Simpson rule here. So we have the second point here. What this means is, for Simpson, we must have 3 points to start. x1, x2, okay, with 2 interval. And it will added by 2, 2, 2, and 2. So the interval must be even. If you want to calculate in Simpson, the interval must be even. Okay, as I mentioned in previous slide, the n must be even for Simpson rule. Okay, and we have, if you see the equation here, the formula, the final formula here, we have the start, the a and the b. This is the a, this is the b, and we have some f that multiplied by 4, some f multiplied by 2. Okay, so if you remember the previous trapezoidal rule, we have 2 columns, right? One for the start and the end, the a and the b. Okay, one for in the middle. But for Simpson 1/3 rule here, we have one column for the one that multiplied by 4, one column for the one that multiplied by 2, where the n is even. So the n must be even for Simpson rule. Right, that's the end of the Simpson 1/3. This one is Simpson 3/8 rule. Okay, if you remember, we still use the polynomial, right? This is from the trapezoidal. Okay, and in the 1/3, we add this point, okay, with this degree 2. And for 3/8, we add one more, which is point number 3, the degree number 3 here. Okay, so we have 3 degree. So before this, our x is x0, 1, and 2, right? Now the x we need to have 4x, x0, x1, x2, x3. Okay, so we have 3 trapezoidal. Okay, that's why the n is 3, the multiple of 3, 3, 6, 9, 12, 15, 18, 21, and so on. Okay, this equation is called Simpson 3/8 rule because h is multiplied by 3/8. So this is why it is called the 3/8, because h is multiplied by 3/8. Okay, if we still have 3 columns, okay, the first one is for your a and b, right? The second column is multiplied by 3 here. The third column is the one, the I, 3, the multiplied by 2 here. Now, the second column is the number that is not the multiple of 3. Let's say if you have until 12, right? For 1, 2, 1, 2, the n1, n2, 4, 5 will be in this column. But for this one, the n is the one is multiplied by 3. 3, 6, 9, and so on. Okay, I will show you in the example. Okay, now let's look at the example. They ask us to approximate the following integrals using Simpson 1/3 rule. Okay, Simpson 1/3 rule with h 0.5 and h 0.25, exactly the same equation as before. Okay, they give us also the fx. They also can give you a table instead of the fx. Okay, it depends on the question. Okay, right. So we have our h, right? 0.5, so you can find our n. The first thing, the first criteria to use the 1/3 rule, make sure the n is even. So if we calculate our n is even, right? So our n is 6. And we have 7 points, including 0. So 0, 1, 2, 3, 4, 5, 6, 7 points, but our n is 6. So we can use 1/3 rule. Same as our trapezoidal, this is our A, this is our B, and this is our H. Okay, which is 0.5. And this is the equation based from the question. So you put into the equation 1.0, 1.5, 2.0, and you get your answer. Okay. But the only difference here, we have 3 columns instead of 2. The first column is still the same. The A and the B, the first and the last. So we have the sum. For the second column is the odd number. If you see the I here in our n, 1, 3, 5, odd number, right? Odd number is in the second column. The even number 2, 4 is on the third column. Okay, so we get like a zigzag here, right? Let's say we have until 8, right? Until 8 we have 7, let's say. Okay, so our 6 here, this one will be here, right? And our 7 will be here. Our 8 will be the end, the last one here. Okay, so as long as you have even number, you need to put in the third row, the third column. The odd number, you put it into the second column. But the last one, the 8, the 6, if you have 4, is the last one, will be on the first column, the last one. The first and the last always on the first column. Okay, followed by the odd number, followed by the even number in the middle. Now, next part is just put into the equation. Okay, this is your A and B, the first and the last, right? This is your sum of the odd number. Okay, and this is the sum for the even number. Then you put into the equation the sum, and then you will get your approximation. Okay, the next one is for h 0.25. Same thing. Okay, we must first consider the n. It must be even. So when we do the calculation, we get our n is 12, so our n is even. So we can use this 1/3 rule. Okay, this is your A, this is your B, and because of this 0.25, the h, so you have so many more n. Okay, this is your h. And then put your here inside the fx, so you can get the answer. Okay, and then you see for odd number 1, 3, 5, 7, 9, 11, all in the first column. You put it into the first column. Okay, the odd number. The even number in the middle will be on the here on the third column. 8, 6, 4, 2. Okay, but the last one, 12, because it is the last one, it will be on the first column. So you have the sum of the one and the last, the first and the last, and then the sum of the odd and sum of the even, same as previously. Okay, next, this is the easy part. The easy part, we insert the h 0.25 and the sum of the first and the last, and then the sum of the odd and the sum of the even. Don't forget to multiply, okay, because this is based on the equation. Just follow the equation. Okay, and then you will get your answer. Okay, now they compare the result of Trapezoidal Rule and Simpson 1/3 rule. So you can see the exact value is 2.8925. So you can see the 1/3 rule, the approximation is most accurate, more accurate compared to the Trapezoidal Rule. Okay. Okay, now we go to the example of 3/8 rule. Same questions. This is the fx, same fx as before, but now with h 0.25 only. Okay, we try to see how to answer this. Again, make this table, the 3/8 table. It will consist of 3 columns. Okay, so first you must make sure that your n is 12. Okay, your n is a multiple of 3. So this is 3, 6, 9, 12, 15, and so on. Okay, so we have 12. N is 12. Okay, n is 12. So here, so we can use the 3/8 rule. Okay, you must consider that first. Okay, your n must be multiple of 3. Okay, now same thing as before, A and B, first and the last, and this is your H. Okay, you need to make this table, okay, this column. Then you calculate your answer by putting 1.0, 125, 1.25 inside this equation. Okay, this is based from the question. The question will give you. Okay. Now, the thing difference here is the where you put the number here. If you see 3, 6, 9, this is all the multiple of 3, right? 12, but 12 is the last one. So we know that the first and the last will be here. The first and the last will be here. Okay, so all the others in the middle, in the multiple of 3, 3, 6, 9, it will be on the third column. Okay, remember this one is quite tricky. Okay, you need to be very careful. For 3 over 8, look at the multiple of 3. 3, 6, 9. If you have, let's say, 13, 14, 15. So 3, 6, 9, 12. 12 also will be here. If you have until 15. But 15, although it is also a multiple of 3, but it is also the last one. Right? So the last one will be in the first column. Okay, you disregard the first and the last one. In the middle, if you have a multiple of 3, 3, 6, 9, for this question until 12, so multiple of 3 inside it, 3, 6, 9, it is on the third column. The rest, 1, 2, 4, 5, 7, 8, 10, 11 is on the second column. Okay, that's the difference between 3 over 8 and 1 over 2. 1 over 2, 1 over 3, sorry. For 1 over 3, you just odd and even. Okay, but for 3 over 8, the multiple of 3 in the third column. Multiple of 3, 3, 6, 9 in here. But for other numbers, 1, 2, 4, 5, 7, 8, 10, 11 here on the second column. If let's say it stopped until here, let's say your n is 6. Let's say your n is 6. So 6 is also multiple of 3. So you can use the 3 over 8 rule. So let's say it is until 6. This one, even though it is multiple of 3, right? But this one is the last one. If your n until 6. So this one will be here. The first column. Okay. So disregard of the first and the last column. In the middle, you must find the multiple of 3 to be put into the third column. Okay. Then you sum it up. This is the easiest part, the easy part that you just put into the equation. So we have our 3h over 8. So you put your h here. This one is your a and b. Okay, the first and the last. This one is the sum of the middle that is not the multiple of 3. Okay, don't forget to multiply by 3 also because it is in the equation. This one is the multiple of 3. Okay, the sum of multiple of 3 in the table. Don't forget to multiply by 2 because this is in the equation. So you will get your value of approximation here.